lot to live up to in that introduction. It's like part 2 of Adrian's keynote this morning. I hope he doesn't mind the comparison. So let's talk about complex systems. My name's Casey. A few months ago, I worked at a small startup called Netflix. And they have a streaming video service. If you have a mobile phone, laptop, something like that, you can make a request to their service to watch a video, and that request comes in and hits a microservice architecture. Here's a picture of it. They have 7 microservices. Your request comes into microservice C, and because it's a microservice, it doesn't have all of the information it needs to respond to your request. So C reaches out to A and F, and they're also microservices, so they also have to reach out for additional information. So A reaches out to B and D, and F also reaches out to D and to G, and then G and D reach out to E, and then E reaches out to A, and they all get their little pieces, and in their replies to each other, they amalgamate this request, and finally the response is emitted back to your device. I don't know if you see a problem here, but there's a lot of communication between these different microservices. And I fibbed, there aren't 7, there's closer to 100 in the streaming path just to be able to watch a video. One of the teams that I managed built this tool to visualize it. So why would Netflix do this? They did it to get feature velocity. What they did was they structured their engineering org to be more like say 100 small engineering teams of like 5 to 7 engineers each that can act autonomously and be responsible for their own pushes to production, their own feature development lifecycle, all of their operational concerns for their microservice. And that way, they don't have all this coordination to make sure that features wait for each other. If you own a microservice for, say, the movie database, you can just make changes and roll it out, and you get those features rolled out as fast as possible. But there are problems with this. If you're interested in a long litany of problems in me describing the water that we're drowning in, I spoke at GOTO 2 years ago and focused a lot on some of the problems of complex systems like this. But I'll give you a quick example just to prove that I'm not lying. So imagine we've got this microservice setup, very simple. P stands for, I don't know, people, and Q is some sort of like persistence layer. So a person object comes into the microservice P, and it says, OK, Q, please store this for me. And Q saves the data into a persistent column store and also into Redis cache. And then when we want to read the information for that person back out, it just goes the other way, except Q is going to read it out of Redis first, and if it has it, great. And if not, it'll have the fallback of getting it from the persistence layer, the column data store that's persisted. And to add to this, to add a little bit of resilience to this, we'll put fallbacks in place so that if there's a problem with Redis, Q will reach out to the persistence store. And if there's a problem with both, it'll just pass a default onto P. And if P gets an error from Q, or Q doesn't respond, because that's the thing that happens in distributed systems, you'll have network partitions and things like that, then P will have some situation, some fallback to handle that. So this is in production for a while, and then one day Redis catches on fire and goes down. So OK, Q has an exception for this. It'll get the data for this person from the persistent column database instead. Unfortunately, this has been in production for a while, so people building applications that use these features have extended the read path a lot. And since Redis is fast, this configuration has kept up with that. But now when Redis is down, we discover that the column store isn't fast enough to keep up with all the traffic that it has now. So it gets slow. And some exceptions start getting triggered, and Q says, OK, so I'm going to pass. Things are starting to get a little bit wonky. Fortunately, we thought of this ahead of time. So I'm going to pass a 404 onto P. There's a problem with that, though. In this setup, logically, we store a person, and then we retrieve it. we never try to retrieve a person who doesn't exist. And we never remove people. So P gets a 404 when it tries to read from a person it knows it wrote. That's impossible. What does it do with that? We didn't think of that. It expected an error from Q or just lack of response. But it didn't fail that way, the way that we expected. It failed in a new way. It got a 404, which is meaningless. So it throws an exception, it crashes, and takes the whole site down. This kind of stuff happens all of the time. You can please take my word for it. And what's wrong here? What's wrong with this design? Well, hopefully, what you've gotten out of some of the previous keynotes and presentations at this point is there's nothing wrong with this design. The people who set this up, they didn't do anything stupid. In fact, they went the extra mile to put in fallbacks. But there's an intrinsic complexity to this distributed system that leads to undesirable systemic output. That's the question. How do we survive the undesirable effects of complex systems? Most of the time, they should do what we want. But by nature of being complex, we know that they're confusing, and that given any specific set of circumstances, it's impossible to predict exactly how the system is going to behave. That's what defines a complex system. It's a little bit bigger than what a human mind can grapple with. So I know what you're thinking. Casey, is the answer simplicity? And the simple answer to this answer in the form of a question to the previous question is no. The answer is not simplicity. Let me explain why. We can divide complexity roughly into two buckets. The first is accidental. I'll paraphrase something I overheard Jorn say once, actually, that nobody brings complexity in on purpose, just like nobody brings dirt into their house on purpose. I actually have 2 kids under 4, so they sometimes actually do bring dirt in on purpose. But assuming like most of us that doesn't happen, dirt just accumulates on the floor out of being alive, and I don't know, it just shows up. And so it happens. The same is true about accidental complexity. Just by virtue of doing work in software and writing code, with the tools that we have, you will create accidental complexity. And here's the bad news. I don't know of any way to sustainably remove accidental complexity. You can do short-term projects to take a very complex piece and remove it with something simpler. That's possible. But over a long-term project, there's no way to, as far as I know, even limit the level of simplicity that you have. And there's a couple of reasons why for that. Basically comes back to the problem that to create a system that controls another system, the controlling system has to be at least as complex as what it's controlling, usually is more complex. And so we end up with a situation where it's just untenable to make things simpler. Now, I've heard that you can get some benefits from simpler systems, and I'll argue that that's not true. There's another bucket of complexity called essential complexity. This is the complexity that we put into things on purpose. Why would we do that? Well, like I said, I've heard that some people say, oh, you know what? The most performant system is the simplest. The most available system is the simplest. Therefore, if you want to make something more available, make it simpler. So take the simplest data store you can imagine, key value running in memory on this very futuristic-looking laptop. And say I want to make this more available. Like when I close the lid to my laptop, I don't want the data to go away, right? I want people to still be able to access it. So what's an easy thing to do? We can put it on the cloud. Okay, everybody knows that one. What else can we do to make it more available? We can add some distributed locks. That was just to rankle Kyle. No such thing as distributed locks. But we can't put it inside of a consistent hash, have a replica set, multiple nodes replicating the data. This is a well-known thing to do for databases. And then we can replicate those cross-regionally so that we've got active-active or master-master setups so that this data is much more available and can even survive, like, say, a regional outage. That's complex. We can get to complexity real quick for the sake of availability. Back to my example. Give me a way to make this database more available and simpler. Don't bother, you can't do it. If you think you have a way of doing that, I would love to hear it, but the burden of proof is on you because I don't think you can. So essential complexity is complexity we add on purpose for these things we want to optimize for, like performance and availability and other interesting things. So no, we can't just get rid of the complexity. OK, well, you had a lot of redundancy in that slide. Is redundancy the answer? Is that how we make systems safer? Kind of, sort of. Despite designers' best intentions, redundancy can unwittingly increase the chances of an accident by encouraging operators to push safety limits well beyond where they would have had such redundancies not been installed. This was true in the case of that quick example I had of people relying on Redis, the redundant cache there, and not realizing that they had overrun the safety limit of what the persistent column store was able to serve in terms of requests per second. Snook has an example. We'll keep with the air travel examples. He has an example of a military helicopter that has 2 motors for each rotor. In case one breaks, they've got the backup one, so they'll be OK. So what do the pilots do? They run the helicopters faster and harder and over spec for any single engine because they can tell they have the extra power there, which, of course, makes it less safe. So redundancy by itself can help, probably not the answer, though. Is it observability? Maybe we just can't see enough into these complex systems, and if we could see deeper into them, we could solve our availability issues. There's something to this, but again, this isn't an entire solution. There isn't much that I agree with James Reason on, but there's something in here. Other things being equal, blah, blah, blah. The number of bugs that a tightly coupled system is likely to contain is greater. However, simpler systems are more transparent, and thus relatively few bugs can wreak greater havoc in simpler systems than more advanced ones. So it turns out complex systems, because they've evolved, it's harder to bring them down because they have more ways of recovering. So in simpler systems, it's easier to bring them down with like one critical flaw. But it's also easier to observe simpler systems. The converse is true. So if we want to make a system more available, we make it more complex. That also makes it less observable. So we kind of can't have that cake and eat it too. Oh, chaos talks. So my screen is blinking. OK, so maybe we can change these types of complexity and control something there instead of if we can't get rid of complexity and we can't like just brute force engineer our way out of this problem, maybe we can change the shape of complexity. So there's this theory, the economic pillars of complexity. It comes from economics that says there are these 4 properties: number of states, relationships, environment, and irreversibility. And when you're manufacturing something or maintaining it in a production line, these are the 4 things that can add complexity and difficulty to your life. The quintessential example here is Ford from the 1920s, 1930s. You can have any kind of car you want as long as it's a Model T in black. So they drastically limited the states of product that they produce. It gives them a lot less to worry about. And then instead of having teams that build a car, they implemented Taylorism wholeheartedly, and they reduced the relationships, the interdependencies between different parts, and just had assembly lines. And so a person could maybe talk to the person to the left and maybe to the person to the right, but they couldn't do a lot. They couldn't move around a lot. So by limiting states and relationships, they scaled out a very complex system very well. Now in software, usually there's a strong pressure to increase the number of states because that corresponds with features. And the movement of the industry right now is to increase the interdependency between those pieces, the relationships, because microservices, containers, serverless, these all make it, they reduce the friction of putting stuff into production, so they make it easier for small things to communicate with each other. So I don't think we can do much with that. Environment, you can't do anything about, but irreversibility. Now, software has some solutions here, starting with the movement of the industry, say 2 decades ago-ish, from waterfall production to XP agile stuff. Irreversibility is, it's inverse reversibility. Can I make a decision and then quickly go back and try something else? So waterfall, you spend all this time documenting it, planning it, then you spend all this time building it, then you put it in front of the customer and they say, no, that's not what I meant. That's irreversible, that's hard. Agile small sprints, you do something, show it to the customer, yeah, that's right, yeah, that's right, yeah, that's right, no, that's wrong, oops, back up, try something different. We extended that through engineering into continuous delivery, continuous integration, testing practices, TDD, and again, serverless and containers by reducing the friction to publish stuff into production increases our ability to reverse our decisions. So that's one way that we can kind of sort of control the complexity that plagues us by diminishing the irreversibility or by increasing the reversibility of our decisions. Canaries, blue, green, or red, black deploys, depending on your terminology. These sorts of things can help you tame some aspect, some kind of the complexity that you have to deal with in our world. Okay, continuous delivery, continuous development. It's a lot of automation. Is that the solution? Humans are notoriously bad at monitoring systems that rarely fail. About a month and a half ago, a pedestrian was killed by an Uber car, autonomously driving vehicle. As Adrian mentioned this morning, we almost have this primal need to pin it on a person, right? Oh, there was a they call it driver, but it wasn't really a driver. There was an observer in their driver's seat. That person failed. They've lost situational awareness or some other make-believe thing that you can't measure. The truth is, there's nothing that the person in the driver's seat was doing in the seconds before that accident that person wasn't also doing 5 minutes, 15, 20 minutes before the accident. So whatever that person was doing didn't cause the accident, because that variable didn't change. So no, we can't just automate our way out of the situation. Elon Musk famously said 2 weeks ago, maybe, that he underestimated humans, he over-automated Tesla, and that led to a lot of their manufacturing issues. The Japanese and lean processing already had this kind of figured out. You don't automate something unless you have a lot of experience doing it manually first. And if it's really well understood, then you can automate it. This is a complex system we're talking about. We don't really well understand anything. So automation will not dig us out of this hole. It will not give us the security and safety that we want. What about training? If we can't engineer our way out of this, is there some way that we can just make the humans smarter? As a response to an incident or an accident, put them through training is an organizational odor, like a code smell. Just pay attention to this next time you see an accident and you see a company fess up and they're like, oh, we're going to put them through training. Starbucks did this a week and a half ago when they had a racial profiling at one of their stores in Philadelphia, and they're like, oh, we're going to put 8,000 of our people through training. That'll fix the problem. Spoiler alert, that will not fix the problem. Almost always, this is a sign of a lack of alignment at an organizational level in the company. So putting them through training is not going to solve. You can't teach people better alignment. That doesn't work. What about compliance? Can we just force people to always do the right thing and never do the wrong thing? Following the aviation examples from this morning, there's this one study that Decker reported on where scientists sat in a cockpit and had all the procedures, and they just watched pilots go through their day, and they would just count the times that they screwed up. And they noticed that some of the more experienced pilots would screw up more often than the less experienced pilots. I thought, that's interesting. They went back and did it again later, and then this time they asked the pilots, hey, did you notice you just screwed up? You violated this rule. And the pilots would go, yeah, but you didn't see this over here. I'm actually adjusting to this other situation that I know is going to happen, and there's no rule for it yet because regulation is not something you could do before the fact. Best practices are not derived. They are subjective attributions. Best practices are after the fact described. So you cannot say before the fact, these are the best practices, make everybody follow them, because you won't have them until experienced people actually do the things. Switching gears a little bit, I know chaos engineering has been mentioned so much at this conference, it makes me happy. So Netflix ran this experiment where they moved from the data center to the cloud. The site suffered because instances would disappear, so they implemented Chaos Monkey to turn instances off. Why did they do that? Well, all those small engineering teams, they had no architect who could force all of the engineers to use best practices to circumvent a single point of failure. So instead, they took the problem, put it right in front of the engineers, and said, you're not getting anything done until you solve this problem because it's going to turn one of your instances off at least once a day. It modified their behavior by aligning them. Worked on small scale, so then we did it on the large scale. We said, OK, we're going to turn a region off so that we can survive that. Well, for some reason, Amazon doesn't let Netflix turn a region off, something about other customers being there. But they simulate it very well. So, like Adrian mentioned earlier, I managed the team that got that down to 6 minutes. So that was a very smooth transition. Why does that work? Economics, workload, and safety. This model was mentioned earlier. Imagine you're walking through a tunnel. This is your life as a software engineer. Hopefully there's a light at the end. And one of the walls is workload. Let's say the roof is economics, and another is safety. And it's like that game Operation. If you touch any of the walls, bzz, you're done. So like economics, the boundary there is if you run out of money, you're done. Most of us have an intuitive sense of like, oh, my time costs money, computers cost, AWS resources cost money. We kind of get that. We kind of know what the economics are. Most of us kind of know what workload is like. Oh, I'm too busy, I'm burning out, I can't get all this stuff done. These computers can't handle all of this load we're giving them. We have no signal for safety. So what happens as we're walking through that tunnel is we go, oh, economics is up there, workload is up there, and you walk right into the safety wall. You don't know you're unsafe until you hit the wall. So the reason chaos engineering works is because it creates that signal for safety. It's the facilitation of experiments to uncover systemic weaknesses. When I first took over the chaos team at Netflix, we had Chaos Monkey, and I went around and asked, what is chaos engineering? And the answer I most commonly got was, oh, that's when we break stuff in production. That sounds cool, but I guarantee you that if you gave me root access to your production environment, I could break it in a way that you wouldn't be happy with and you would learn nothing from. So that's kind of the naive approach. And then there was a couple other ideas, and we said, you know what? We really need to understand what we're doing here, how it works, so that we can know when we're doing chaos engineering, but also how to do it better. So now we know. We do it better by running experiments to create that safety signal to tell people you're getting too close to that wall. That helps give you better availability. We defined it, wrote it up, Principles of Chaos Engineering, principlesofchaos.org has a write-up. CHAP is the most sophisticated implementation of chaos engineering that I know. At Netflix, it is the chaos automation platform. They blog about it. It's really cool. And that runs chaos experiments constantly to constantly tell people, oh, I found a safety edge over here. And that gives people the signal, oh, we're running too hot, or we need to spend more time, or we need to fix that particular thing. Or think about this resource allocation issue that we hadn't previously thought about. So back to the question, how do we survive undesirable effects of complex systems? I'm not going to give you an exact answer, but maybe I'll give you something to think about and some advice. And if you think you have the answer, you can come talk to me. Otherwise, I'm going to keep the real answer in my pocket. But think of a well-run kitchen. Hopefully, you've had this experience where you and other people have been in a kitchen, and you're all making stuff, and you're walking around each other, and you're doing things, and somehow dinner ends up happening. And hopefully, you've had this experience where you finish what you're working on, and then you stop, and you're done with your part, and all of a sudden, you're in everybody's way. And whereas before everybody was seamlessly moving around, now you can't figure out how to get out of everybody's way. Why does that happen? Well, part of it is because everybody unconsciously had a mental model of what it was that you were doing when you had a task. And humans are good at this. And when you stop doing something, subconsciously, everybody else lost their model of what it is you're trying to achieve. And now you're just an obstacle. So here's some advice to survive complex systems. Embrace the complexity and navigate it. Don't try to remove it. You're going to frustrate yourself and waste time. Provide opportunities for teams to practice working together. This might be game days or fire drills, or it might be more meaningful long-term engagements. People working together figure out how to solve these problems in ways that you cannot prescribe. You cannot write it down in procedure. Tolerate inefficiencies. As software engineers, we love to talk about how efficient we can make things. Really efficient systems are really brittle. Ha! So if you want a system that can survive outages, it's going to have inefficiencies. That flexibility is part of what makes it safer. And communicate the safety margin. Find ways to communicate that safety margin that's often silent, that you don't want to accidentally run into. And here's my clue for the real solution to all of this. Humans create resilience, not tools. I wrote a book on this with the rest of the Chaos team at Netflix. We'll be giving away copies around 2:33 at the O'Reilly booth. Come talk to me about that. That would be cool. I work for a company called Backplane. This time next year, you'll probably know what we do. Questions?
I think we should first do a round of applause.
Thank you.
So I'm so sorry to do this, but we ran a little late. So I only have time for a few questions.
I can answer more questions at the O'Reilly booth, too. Happy to do that.
That is a great troubleshooting approach. Thank you for that. And I don't know if it's maybe everyone's downloading chaos engineering resources right now, but my Wi-Fi isn't working, so I can't see the questions. So why don't we just end it for now? Can we do one more round of applause for Casey?
Thank you.